Hi everyone, I'm David Gerault. Welcome to this presentation of our paper Mechanized Models and Proof for Distance Bounding. This paper is about distance bounding protocols where a prover P authenticates to a verifier V on a shared key X. These protocols have an additional distance component such that if a prover tries to authenticate from a distance greater than a given bound, it will not be accepted. For this paper, we had two main questions. The first one was what if adversaries are significantly more powerful than usual? So what if, for instance, the adversary has more than one key, or what if he has more advanced channel manipulation abilities? Does this lead to new attacks? And the answer is yes. And the second question was, can we model physicalities such as time and distance in a computational framework to complete the symbolic work that has been done recently? And the answer to that is yes, we made a model in Easycrypt. Here we have an example of a distance bounding protocol where a prover and verifier start by agreeing on two response vectors R0 and R1, which are computed as a function of two shared nonces NP and NV, as well as the shared secret X. Then we have n challenge response rounds, during which the verifier will send a challenge Ci, which is generally a single bit, and expect a response Ri, which is a bit from R0 or R1 depending on the challenge. Each of these challenge responses are timed, and in the end the verifier will check that the responses are correct and that all the timings are within the time bound, which is a proxy for a distance bound. The classical tests against distance bounding start with distance fraud, where a malicious prover, knowing a legitimate key X, tries to authenticate to a verifier while being outside of the distance bound. This threat is extended to what is called distance hijacking if additional provers are allowed in the vicinity of the verifier, where these provers are honest and running on different keys. Then we have mafia fraud, where two adversaries AP and AV, located respectively close to the prover and the verifier, act as a man in the middle between P and V, trying to make V accept the authentication of P, despite P being far away. And then we have terrorist fraud, which I won't talk about in this presentation. In this paper, we propose a new model called FlexiDB, which inherits properties from the classical BMV and FO model, as well as from recently published symbolic works. For instance, this big mute button comes from the symbolic works, and it allows the adversary to block messages from any of the provers to the verifier and vice versa. So here we present an attack that is not possible in other models with these enhanced adversarial capabilities, and we see that we have an adversary that has his own key X0 as well as the keys to all of the other provers that are near the verifier. The attack goes as follows. The adversary starts a session with V and triggers all the provers to start a session as well, and because the messages are broadcast, the adversary receives the nonces from everyone, which means that because he knows the keys, he can compute the R0 and R1 response vectors from everyone, and then at each round he can determine one prover that has the same two responses as him and block all the other provers. By doing so, at each round, only one prover with the same responses as the adversary will reply to the verifier, and the adversary will be accepted despite being far away. In FlexiDB, an adversary has a combination of party corruption and network corruption abilities. In terms of party corruption, the adversary can be an outsider, which is a classical mafia fraud adversary that knows no keys. It can also be a one-weak insider, which is a classical distance fraud adversary that knows one secret key. Or it can be one strong insider who not only knows but chooses one key. In addition to that, we propose the new notions of n-weak insider and n-strong insider, which respectively know and choose n keys. Now, in terms of network corruptions, we have several levels. We have a dummy adversary that sends and receives messages within his range. We have an amplifier adversary that is able to send and receive messages from afar. And this notion is important to distinguish scenarios such as NFC, for instance, where the communication is assumed to only take place within range, from different scenarios where the adversary is able to eavesdrop messages from a distance. Then we have the injector adversary that is able to send, receive, block, and overwrite messages within range, so messages that are initiated close to him. And finally, we have a full adversary that is able to send, receive, block, and overwrite messages even from a distance, which is the most powerful adversary that we have. In our model, all parties have a position in the metric space as usual, where parties are provers, verifiers, or two adversarial entities known as AP, the adversary that is close to the prover, and AV, the adversary that is close to the verifier. Which of them is present depends on the threat that we are considering, and the adversary is parameterized by channel and party corruption abilities. And this is fine-grained, so an adversary can have very strong channel modification abilities and very weak party corruption abilities. So an adversary is a combination of these two abilities. And finally, we have a challenger that provides an environment for A, in which we carry the proofs. And this challenger provides oracles such as join that allows the adversary to register new provers which are either corrupted or not, to move parties around, to replace messages or part of messages at a bit level granularity, or to start session and various other bookkeeping oracles. The first threat we model is GMF, or Generalized Mafia Fraud, which, similar to mafia frauds in the BMV model, has a learning phase. So we have the adversary interacting freely with everyone and then outputting a location for AP and AV, as well as a designated prover and a designated verifier, which will be the targets of the attacks. Then the challenger checks that everything is in order, and the adversary wins if he can make V accept the authentication of a prover for which the adversary does not have the key, and such that the prover is far away. In this scenario, we didn't find any new attacks except for very exotic toy protocols, but the interesting thing is with GDF. GDF is for Generalized Distance Fraud, and it generalizes both distance fraud and distance hijacking. In this setting, we only have AP, we don't have AV, because the adversary knows the secret key of the designated prover, so we can't have an adversary near the verifier. And here, in this model, we find new attacks. One is the motivating example presented at the beginning of this talk, which is a N-weak insider full GMF. We also have an extension to the PRF programming attacks proposed by Ioana a few years ago, which is a one-weak insider full GMF, where we show that the ability to replace parts of the messages enables attacks on proven secure protocols. Then we have attacks on terrorist fraud resistant protocols, which are one strong insider amplifier attacks, and a new attack on the EMV RRP v2, which is a variant of a standard contactless payment protocol. And just one word on this, it does not threaten the actual protocol because it's one weak insider, so the adversary knows the key attack, which is not the case in contactless payment. And it's also a full attack, which means that the adversary can communicate from afar and receive messages from afar, which is not the case in contactless payment then again. But it's nonetheless an interesting theoretical attack. Now, how did we mechanize this in Easycrypt? Well, we have Easycrypt modules representing the environment, the prover and the verifier for a given protocol, and the oracles related to this prover and verifier that are provided to the adversary. Regarding the environment, we have time that is measured on a global clock with reals, and that is accessed through functions getTime and addTime, such that addTime is only triggered by adversarial actions. We have locations that are reals in a 1D space with accessors, and with these modules, we model a form of outsider full GMF adversary that we test on the EMV RRP contactless payment protocol, such that we can prove its security. And this is a restricted version of the model that I presented before, but it's a proof of concept that we can use time and location in a computational framework. In conclusion, we proposed new attack models for distance bounding with granularity on the choice of party corruption and network corruption. And this granularity is interesting for application designers because when you want to prove a protocol, you don't want to be bothered with use cases that are not yours. So for instance, if you have tamper-proof devices, then you don't need to worry about the adversary knowing several keys. And our model works quite fine for that. Using this model, we found new attacks with a stronger adversary that may be too strong, especially because one of them applies to most protocols, but that are still interesting for future application. And we also provided a mechanization of this model in Easycrypt, which is a proof of concept. And within this proof of concept model, we could do proofs for the GMF security of the EMV or RP protocol. Now I'm running out of time, so I will thank you for your attention and answer questions.